Mr. Schultz here with you. We're going to take a look at 11.2.3, problem or section 11.2.3, which is going to be talking about quality control. So how can we use what we've been doing with sample variability to find out some quality stuff? So let's see what's going on. When companies accept items for shipment or distribution, they often do not test every single item for quality. In many processes, testing every item will be far too time consuming and expensive. For example, when testing a 2-liter bottles of soda for bursting strength, sometimes testing destroys the item. If companies tested every item, there'd be nothing left to ship. Instead, quality control testing is done on a small sample of items. The sample does not meet the quality standards, the entire batch is thrown out or recycled. So we're going to simulate some of that with some dice. So let's take a look at our next problem here. Going to look something like this. Your task is to assure quality control for PCI Probability Cubes Incorporated. The quality of their product is critical for the success of PCI. Plan to take 10 dice out of each case and test to see whether they fall within the company's specifications. If the dice fail to fall within the acceptable range, the entire case will be thrown out. First, we need to determine the acceptable range for well-functioning dice, and we're going to use a simulation, and we're going to do that right now. So let's jump over here to our ideas here. So one, we've got our CPM tool, which would be something like this. So you would get, so this would be your first 5 dice that you'd be rolling. Here would be your next 5 dice that you'd be rolling. Then what you do is you'd have to add up all these numbers and divide by 10, or just move that decimal point. And that would get you, well, I guess I might have gone a step too far here. So let's see what this first step says here, and then we'll jump back in that tool more. It says work with partners, set up a simulation for rolling dice, record the mean. So that's what I was jumping into there. So this is one tool here that you go and you would do your rolls there. We have one in decimals as well. The numbers 1 through 6. We're gonna get a random group of 10 numbers there. You can also do it on your TI calculator here. Just math, probability, random integer, and so on and so forth, upper and lower bounds, all that fun stuff. Save it to the list. And I've already done all this, so I've saved it to the list here, my 10 items here that I've got the 10 rolls. Okay, sweet. So we've generated that. So the second part said to make it to do an average. Let me show you something on the TI here, but you can do a thing here where you go to apps, or excuse me, not apps. You go to stat, and you would go over here to calculate one var stat, meaning one variable here. So I just do that, and I take my L1 list, I put that in there, and then I'm just going to go down and calculate, and it's going to give me what that average. So it's X bar, that's the same thing as the average. And there's that. It's also got a bunch of other stats here. So it's got like the minimum, the Q1, the medium, the Q3, the maximum. So real quick way to make a box plot there, the number of items in that list, so on and so forth. So kind of a cool thing here. The CPM one just basically tells you to do it by hand. Just add up the pairs that make 10. So 10, 15, 17, 20, 3, 6, 9. So this would be 30. So this is a 3.0 average this you, or you can do it in decimals, where here's my difference that I've got that you might have noticed when I showed it to you the first time. I've got this equals L1. So this says, hey, this is my L1 list, and I just want to find the mean of L1. And here's the cool part about that is that now when I do a new random, click that, hey, look at it, auto calculates the list there for me and the average. So I just feel like this is my best tool. I'm going to stick with decimals for this time, but I wanted to show you guys the rest of that stuff so you kind of knew what we were talking about here. So record the mean of the 10 dice. Well, on this roll, we got 3.6. So let's do that. So we got the mean is 3.6. Okay, now have each person in your team run 5 simulations of these dice. Well, okay, we can do that. That's not too hard. So we got 2.5 as our first one. So I'm going to write this down on the iPad while I do this. 3 is my second one. 3.6. We've got 3 again. We've got 3.9. And this is what, 1, 2, 3, 4, 5. So we've got all 5 of them here. Probably can't read that super well. I was trying to do it fast. So 2.5, comma 3, comma 3.6, comma 3, comma 3.9. So we've got our 5 samples here just on Desmos by hitting that random. Then it says combine those results with the results of your classmates and make a histogram. What's the sampling mean of the distribution? So here's what you'd be doing in theory. You would be pressing that 100 times and making a list of 100 things. So so a way that I could do that is, and I would recommend doing it like this, I'd make a new list. So I call this L2, and I just go, okay, 3.9, comma, I'm gonna shuffle it again, 3.2, comma, 4.2, comma, 2.9, comma, and you would go through and you'd end up making your list. Now, this is going to take a while to get you to 100 to 100 things here. What is wrong with my list right now? Um, Oh, I forgot to put a comma here. There we go. Um, and yeah, you can see that I'm at 6 items here. And so then I would just keep going, 4.8, and so on and so forth. And you guys are going to get to watch me type in 100 numbers here as far as an average goes. Just kidding. I am not going to do that because I actually already did that once. Right down here, I made my new list. So what I'm going to do is I'm actually going to have this linked in the Google Classroom, so you can just get and grab my list, from there, so that you can see what's going on without having to get 100 of these means going here. So basically, then what we're going to do next is I'm going to delete out a whole bunch of these so we can get our list up closer, so we can see what is going on here. So we've got our list. Now our next step here is to make a histogram. Again, this is pretty easy in Desmos, especially when you've got things labeled in lists. So I've got this L5 here. So I'm just going to go, hey, I want a histogram, and true to form. If I'm making a video, I cannot type it correctly the first time. Okay, cool. Here's our histogram. Now, this is not a super helpful histogram because you'll notice that it's just counting anytime that I've got something within the twos, it is counting that. So that's that kind of bin thing. Or I could center left and go from 1 to 2. Well, then it's gonna be based on that. Well, here is a nice little thing that'll actually help you in the next part. You can set your bin width, and I'm going to set it to zero point 0.1. So that now, anytime that I've got something that's between 0 and zero point 0.1, which of course would not be possible here, then it'll put it right there. So, here's 1. So it looks like I've got a 1.9. It is right there. If we center this thing, yeah, so that 1.9, I think that actually the left view is kind of my view of choice right now. But so this will give you the count here. So I had one of them that was at 1.9. Maybe I just need to zoom in just a little bit more here for my brain to comprehend this. Yes, okay. Here we go. So here's 1.9. I had one of them there. I had one of them at 2.2. I had one of them at 2.3, and so on and so forth. Here would be what, 2.7 is my guess. It looks like I had a bunch of 2.6s. I had three of my two, or excuse me, not two, of my 4.7 and 4.6. I had three 4.6, one 4.5, one 4.4, so on and so forth. So it's kind of helping me get my counts there. So you don't have to do it like this, but this is how you'd make that histogram there. So let's see what the next question is here. What is the mean of the sampling distribution here? We'll come back to that in just a second. Um, but uh, but or actually, let's just do that now. So then, my next thing, I just need to find what's the mean of L5. There we go. 3.46467. So for all intensive purposes, we could probably call that a 3.5. But yeah, we can go 3.467 there. So we're gonna write that down here. We've got 3.467 as our mean of all those samples there. Okay, now it says find the upper 5% and lower 5%. Oh, this is gonna be terrible, right? Except not, because we changed our histogram bin so that we can actually see the counts there. So here I know that I've got one at 1.9. I've got one at 2.2, 2.3. So, and then I've got a bunch here, four that go up to whatever this number is, 2.5. So I made a list of these things down here. So I had one at 1.9, one at 2.2, one at 2.3, and then three of them there. And then there's actually four. But since I just need the 5% and it's a 100 element list, I'm going to dump one, two, three, four, five numbers. And then, of course, I find the average or the midpoint between these two, which is going to be the same number. So 2.5 is going to be my lower bounds. So I'm just going to write that in actually on my iPad here. So my lower is going to be at 2.5. My upper I will find next. So my upper, same type of thing here. I'm going to go. So I've got one at 4.7. We already checked this one. I've got three at 4.6, and I've got one at 4.5 and one at 4.4. So again, 4.7, 4.6, 4.6, 4.6, 4.5. Here's my 1, 2, 3, 4, 5. So then I'm going to find the average between these two. So my upper here is going to end up being 4.45, which I just wrote that down on my iPad right there because I'm finding that average or that midpoint between these two pieces of data there to get that 5% number. So I've got my upper and my lower there. I've got my mean. I'm all set to make to make the distribution there. So just for the sake of doing it, I would think my dice would be at 3.467 plus or minus the difference between these two numbers. So I've got 4.45 minus 2.5. So I see that as being what? 1.95. If that's correct. Nope, a little bit less than that. Nope, that is actually right. So 1.95, and then I need to split that in half. Boy, this is always fun to do math live. So let's just not do it live and let's do a calculator here. 2.5, double check my math there. That looks good. And we're going to divide that by 2. I'm going to find out it's 0.975. Probably should have been able to do that in my head, but doing math in front of people is always a little bit crazier. So this is our expected values that we were thinking, or expected value is the wrong word there. This is our margin for error here. So basically, this is telling us what we think the range should be if we were to do this. Now, we don't actually have to do this part of the process, but I just wanted you to see that, so I'm going to erase that there, just so you can kind of connect it back to the other learning there. So let's see what they actually want us to do now with this piece of information. This is really all that they need us to do is find what's the upper and lower bounds there in the 90% range there. So, consider the bounds you found to be the upper and lower bounds of the normal manufacturing process of 10 dice. A set of 10 dice does not fall within this range and will be considered defective, and the entire case will be thrown out. So, looking back at that, we had 4.45 and 2.5. So we're thinking that anything in this range is legit. Anything outside of that range is going to be considered a defective box and needs to be thrown out. So your teacher is going to have more samples of dice, and from each case, you will roll the 10 dice and calculate your mean roll. Does your batch fall within the quality control bounds? If not, I will need to discard the entire case. Okay, so we could jump back here, and then you could jump to your CPM tool and do this. I'm again not going to do that there. I'm going to end up in Desmos here, and I am just going to and say this is my new dice that I just gave you, and I'm going to do a random test. 3.1, so this one would stay. I'm going to do this one 3. That would stay. That would stay. That would stay. That would stay, and so on and so forth. Because I'm looking for anything that's above 4.45 or below 2.5. So let's just go until I find one here. Getting a bunch of not good ones. Oh, so here's one. So here's a 4.8. So this box of 10 dice then from the shipment, we would expect this to be bad, and so we would throw that whole shipment out. That is basically what it is thinking. Um, then from there, you would repeat that and do it for a bunch of samples here. So let's jump forward and see what the kind of final part of this process is going to be. So it's asking how many of the cases were rejected by the quality control engineers in your class. So you would basically have just gone through here, and we threw out one out of, you know, two, three, four, five, six, seven, eight. Okay, there's one that's over nine. Um, so in this short little like 10 sample here, we threw away two out of the 10. Now that is a pretty small sample size, but if you started to play this out, what percent of the cases do you think would end up being rejected here? So to take a second and think about that. Okay, so we would expect that about 10% of the cases would end up being thrown out, somewhere around there. And why do we think 10%? Well, because remember, we set our bounds at the 90% range. So it's still possible for perfectly functioning dice to fall at that top 5% or that bottom 5%. So we would assume that because we threw out 5% of perfectly functioning random dice, that we would also have to throw them out here for that. Now, it could be that they're perfectly functioning dice, or it could actually be that they're just falling outside of the range. But we would expect us to lose about 10% of our dice there, due to that, due to them being outside of the range here. And where this is going is that obviously you wouldn't do this like with dice, or something like that. You would probably have to set a different quality control limit. So maybe not 5%. Maybe with dice you do something more. Um, more like 1% or something like that. But most companies, I would say, don't end up doing a process like this. Most of this was just to try to see how those bounds like into this. When you get to tomorrow's lesson or next day's lesson, you'll see how companies actually do use this, and they use it in the manufacturer side. So they will actually check the manufacturing like tolerances so that they don't have to go and throw away a whole case or a whole shipment of something or a whole box or something like that they've already made and gone all the way through. They will check it in the manufacturing stage to see like what kind of makes sense there and what stuff should I be getting rid of because it's not hitting our quality standards. So that's a whole bunch of everything. Review and preview as always, we've got two sections left in this chapter. Have a good rest of your day. Bye bye.